Hi, everyone. I'd like to take this opportunity to talk about one of the coolest applications of Taylor series that you're likely to see. Some people call this the most beautiful formula in all of mathematics. I think that is subjective, right? It depends how far you go. There's a lot more beauty to see, and depending on what kind of math you like. I mean, beauty is in the eye of the beholder, so depends on your personal taste, but this one is certainly up there. I think everyone appreciates this formula and thinks it's magnificent. And it only depends on two things that we've now seen in our Calc 2 class. We've seen the Maclaurin series for cosine and the Maclaurin series for sine. Or I could say the Taylor series about x equals 0 for these two trig functions. And if you write out the terms, you've probably noticed by this point that cosine has all the even terms of x, in the sense that, okay, if I plug in n equals 1, plug in n equals 0, I get x to the 0, which is 1. If I plug in n equals 1, I get minus x squared over 2 factorial. And then the next term is an x to the 4th over 4, and an x minus x to the 6th over 6 factorial, and then a plus x to the 8th over 8 factorial. And you get all your even powers of x and your even factorials. It keeps going forever. And then sine kind of grabs all the odd powers. So if I plug in n equals 1 here, my first term is x. My second term is minus x cubed over 3, so odd powers, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. And then I'll say plus dot dot dot. Goes on forever. And what you might wonder is, what happens if I combine these two series? Right? I mean, they look like they line up really nicely, and I could just add them together. And so you might think, okay, cosine x plus sine x is some kind of nice series like that, right? It's like almost alternating in the sense that the first two terms are positive, the second two are negative. Next two positive, next two negative, so on and so forth. So it's not quite an alternating series. What we want to do instead, and this might come out of the blue, depending on how long it's been since you've seen complex numbers, I could do something real weird, and I could multiply by the square root of -1. Right? So all of a sudden this looks like ix minus ix cubed over 3 factorial plus ix to the 5th plus minus ix to the 7th. And then I could try adding those two series. Okay, so this was Euler's extremely weird insight that if I now add these series, something fantastic happens. I think Euler was one of the first mathematicians to really think about complex numbers as useful in the real world and worthy of investigation. And so, okay, what this looks like is 1 plus ix minus x squared over 2 factorial from the top, minus ix cubed over 3 factorial from the bottom, x to the 4th factorial over 4, ix to the 5th over 5 factorial from the bottom. I'm writing it all out for sort of a good reason. You'll see why. Second. Okay, so now some of these have eyes on them, some of them don't, and you're like, okay, all I've done is make it look weirder than if I just straight up added the original two series. But what you can observe is that I has very nice properties. I to the first power is I, whereas I to the second power is -1, right? Because the square root of -1 is I. Then I cubed, well, I just multiply by I, that would be -I. And then I to the 4th would be I cubed times I, which is -I times I, which is -1, which is 1. And then it cycles back. I to the 5th is I to the 6th is -1, dot, dot, dot. The pattern continues. And so what could I do here? I could think to myself, well, this negative sign is sort of like a -1. It's sort of like an I squared. Right? So let me scoot this over. I could think to myself, this series is, okay, 1 plus ix But instead of -1, I could write a plus I squared here, right? In particular, okay, that would be I squared x squared over 2 factorial. And then I could say, well, this negative I is actually an I cubed. This is I cubed x cubed. Oh, I mean, that's looking interesting. There are a lot of 3's floating around there. And then I could be like, ooh, this is like a 1x to the 4th. But 1 is I to the 4th, right? So this is plus I to the 4th, x to the 4th over 4 factorial. And then the pattern repeats in the sense that, yeah, I is just I, but it's also I to the 5th, right? Because every like 4 cycle, you get back to where you started with. So this is now I to the 5th, x to the 5th over 5 factorial. And then minus x to the 6th is the same as plus I to the 6th, x to the 6th, plus I to the 7th, x to the 7th over 7 factorial, plus I to the 8th, x to the 8th, 8 factorial, dot, dot, dot. Now this is no longer alternating at all. It's like all positive terms. And I could write this as a series in a very nice way. I could say this is, so we can write sigma notation, go from n equals 0 to infinity. And I could kind of just say, okay, for a general, this 5th term is just ix to the 5th over 5 factorial, right? So in general, the nth term should be ix to the n over n factorial. And then I think back to one more thing. I guess I should have drawn a 3rd series up here. There's one more important fact that we know. And maybe you can try to guess it. Maybe it's a good thing I didn't write this in here. You could try to guess what I'm about to do. This series should look almost familiar, except for the I floating around there. It should look, pause the video if you don't want the spoiler, I guess too late. It should look like this. Except, of course, we have ix instead of x. So the claim is, this is actually, instead of e to the x, it's e to the ix. And maybe at this point in your mathematical career, you haven't seen an imaginary exponent before. But this is actually a glorious thing. This tells us that e to the ix, right? Look back at the beginning of our equation. E to the ix can be written as cosine x plus I sine x. Sorry, sine x. Assuming you're okay with complex numbers. And why is this so interesting? It means I can do something like this. I could plug in a value for x. Right? Try x equals pi. Apparently, that is cosine of pi plus I times sine of pi. And cosine of pi, I mean, that's just -1. Whereas sine of pi is 0. Okay, the 0 kills the I. This is no longer a complex thing, at least on the right-hand side. And let's add the 1 over. I get e to the I pi plus 1 equals 0. That is what's called Euler's formula, or I guess that's Euler's identity in this case. For a very nice value of x, x equals pi, you get e to the I pi plus 1 equals 0. And people like to say, ooh, it's like all the constants that matter floating around in a single equation. You've got 0 and 1, and from that you can like get any natural number you want. You have pi, which is awesome. You have e, which is awesome. You also have the square root of -1. This is I right here. And so it's kind of mystical. It's especially mystical that you can take an imaginary, like a complex exponent, and then sort of just add 1 to it and get back to something that's totally normal. And if you haven't seen this before, the magic behind the scenes that's happening is you're imagining the complex plane. So you have some imaginary part and some real part. And all your eyes are like up here or down here, whereas the real axis is what you're used to. And what's actually happening is that if you start with any value, say we just looked at 1, asking the question, what is e to the ix? In this case, we were talking e to the I pi, is actually like saying, take this point and rotate it by pi radians. So rotating by pi radians puts you right over here, -1. So e to the I pi is -1 because rotating by pi radians gets you to -1. This also ends up implying, I mean, we could try another thing. I could try x equals pi over 2, say. E to the I pi over 2, just use this formula, would be cosine of pi over 2. That's something we can figure out. Plus I times sine of pi over 2, also something we can figure out. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So this should just be I. And so this is now saying, if I rotate by pi over 2 radians, I should get to I. Right? And looky here, rotate by pi over 2 radians, that's 90 degrees. That does get you to I. Same story if you want to rotate by pi or 3 pi over 2, right? 3 pi over 2 should get you to -I, and you can check in the formula that it really does. And you don't have to do nice things. You can, whatever value of x you choose, e to the ix is rotation by x radians. Which is insane. So a lot of the times people fawn over this identity, e to the I pi plus 1 equals 0. But this is the real beauty behind the scenes, saying that you can represent e to a complex number as rotation in the complex plane. And this ends up having like all sorts of applications in engineering and physics. Pretty much none of modern physics would exist without this. And like whenever people want to do rotations in, say, like graphical software for like video games or something, they could absolutely rotate things with complex numbers. Or you could use quaternions, which are even weirder. But anyway, I like that a lot. I hope you also enjoyed it, and I will see you next time.